Welcome to today's webinar on velocity. Let's start by understanding why velocity is important. With velocity, you need to hit a sweet spot. Too little and you're going to have problems. The pipe will not reach a self-cleansing velocity, which means the system becomes unhygienic. But too much and you're also going to have problems. The water going through the pipe will make noise and eventually the pipe will fail. So as an engineer, if your design causes either of those problems, it's going to be non-compliant, which puts a lot of risk on you and your company's reputation, and it's going to cost a lot of money to fix. No one's going to want to pay that. But don't worry, because these problems only occur for engineers who don't do the calculations. There's nothing to worry about if you do your calculations, so you're in the right place to learn. So starting with the basics, velocity is the speed at which water moves through the pipe. The first thing to understand here is that if there is no water moving through the pipe, there will not be any velocity. But as the pipe connects to a fixture, water needs to travel through the pipe, and this water will move at a velocity. In this example, we've got 1 meter per second. It's important to know that the pipe layout does not affect velocity, so you can add as many bends as you like, and the velocity does not change. But if you add more flow rate, like we have here with the extra fixture, the pipe that supplies the two fixtures will need to move more water. Therefore, the velocity in that pipe will increase. But to confuse things a little bit, even though there's more water going through that pipe, we can decrease the velocity. And we do that by increasing the pipe size. This makes more sense if we look at the formula. So velocity is determined by dividing the flow rate by the area of the pipe that it is going through. So to put it simply, if the flow rate increases, the velocity will increase. But if the pipe area increases, the velocity decreases. So that's why generally the higher the flow rate, the bigger the pipe size is going to be, because you're going to have to keep the velocity down. And here are some useful formulas for you to use when you're doing your next velocity calculation. It's the same formula that we just looked at. So velocity divided by the flow rate. Velocity equals the flow rate divided by the area. But the industry talks in pipe diameters, not pipe areas. So these formulas are just set up a little bit differently, so they're easier to use. And something that catches a lot of people out is that you need to use the internal diameter of a pipe. A lot of pipes are referred to by an easy to say diameter, like here, with the nominal diameter being 15. But for calculations, using that is going to give you incorrect results, because the internal diameter is actually 10.81, and that's what you need to work out your velocity. And use nominal diameters because the outside diameter here being 12.7 just doesn't really roll off the tongue. So just important to be aware of those three different diameters. Then for the recommended velocity limits, it does change between countries, building types, materials, clients, just engineering preferences. So definitely don't take this as gospel, because in any given situation it could be wrong. But generally the limits are for the minimum velocity around 0.7. Any lower, that's when you start to get particles building up in the pipe and over time becoming unhygienic. And the maximum velocity is quite a range. So here I've got it between 1 and 3. The reason I've got such a range is, for example, if we look at the cold water maximums, within a building it's generally limited to around 1.5. Any higher supposedly can cause noise, which might not be desirable in the building. But for the same reason, being outside and the pipe's in the ground, people sometimes design to a higher velocity. And then when you're actually connecting to a fixture, because that pipe doesn't get used too often, maybe only a few times a day, people design to a higher velocity just to keep the pipe size down. Hot water is different though, and that's because at higher temperatures and high velocities, the pipes can erode and corrode. So when the hot water pipe is supplying just the flow side of it, which is going to the fixtures, is generally limited to around 1.2. But for the recirculation, which is in any medium and large size buildings, you'll generally have hot water recirculation. And because that is continuously recirculating, the velocity is generally kept to 1 meter per second, and some people actually like to go a lot lower than that. And then again, for the fixture connections, you can still go higher because it's only used a few times in the day. And specifically important for the fixture connections on the hot is that, say you're waiting for the shower, for the cold water to come through the dead leg before it gets hot, the larger that pipe diameter is, which may occur if you, say, design to 1 meter per second, that means there's more volume of water in that pipe, so you're going to have to wait longer and waste more water before it gets to your desired temperature. Alright, well let's go through some real life design scenarios now so we can make the velocity calculations just feel like second nature to you. Using h2x's design software, let's do some basic examples to understand the fundamentals. So we'll start by just adding a flow source here, and we'll just put in some zeros for the properties. Then we'll just draw a small pipe section, and we'll use a node to add a flow rate on. So we've got 1 liter per second here. I'll just make a note of this. And let's fix the pipe diameter. So let's say, let's make it 15 millimeters, and I'll just enter that again. So we get that. As we click results, we can see that the velocity going through this pipe is 10.9 meters per second. So pretty much through a relatively small pipe, we're trying to get a high flow rate. And to do that, we're getting this velocity, or the water needs to travel at this velocity. Now I'm going to make a change. I'm going to increase the flow rate. And while I'm doing it, just have a think at what you expect the change in the velocity result is going to be. So I'm going to change this to 2 liters per second, and I'm going to keep the pipe size the same. So we have more water going through the same size pipe. So the velocity increases quite significantly because the area of the pipe hasn't changed, but the amount of water having to go through it has, so it has to go faster. And then I'm going to make one more change. So once again, have a think about what you expect the result to be. I'm going to leave the flow rate the same, but I'm going to increase the pipe diameter, the area of the pipe. So it's still going to be 2 liters per second, but the pipe is going to be 20 millimeters. And the velocity reduces quite significantly. That's because the flow rate hasn't changed, but the area in which the water is going through has increased, so there is less velocity. In this example, we're going to look at a more realistic scenario where we have hot and cold water pipes connecting to these two basins here. So I'll just connect these up, and the software will then recognize how much flow rate needs to be calculated to go through the pipes, and then from there can start to look at the pipe size and velocity calculations. So as we click results, the pipes become sized. And the most interesting thing to see here is that we have a 15 millimeter on the cold and 20 millimeters on the hot, even though they're supplying the same amount of fixtures and flow rate. Before I look into it, do you have any idea why that is? The answer is because we saw earlier, or like we saw earlier, hot water pipes have a lower maximum velocity setting generally than cold water. So in a cold water pipe, because we can go up to 1.5, this flow rate is causing us to have a 1.3 meter per second velocity. So 15 millimeters is sufficiently sized. However, in the hot water system, because we're generally limited to 1.2, using a 15 millimeter pipe, that velocity would have been too high. Therefore, it's picked the next pipe size up, which brings the velocity down. Just to show this a little bit more, if we come back here and override this velocity parameter to be even just 1.4, we can see now that just like the cold water pipe, it's gone to a 15 millimeter size because the velocity is only 1.3. And we can look at the same for the cold now. If we decrease this, to say 1 meter per second and click results, it is now a 20 millimeter pipe at a really low velocity. And just to exaggerate, let's say, for example, we could override this pipe diameter to be something really large, like 100 millimeters. And what happens now is, because that pipe, the area of the pipe is so large, that the velocity is very, very low. Now, of course, this would be a really bad design because it's not even close to reaching the self-cleansing velocity. In this example, I want to help you to understand the relationship that velocity has with pressure drop. It's very similar in the sense that the higher the velocity is, the higher the pressure drop will be. So if you increase a pipe size and the velocity decreases, the pressure drop will decrease too. So here we can see that we're getting warnings at these fixtures because we have a recommended minimum pressure of 200. And on the hot, we're getting around 220. But on the cold, we're getting less, 190. And the reason for that is because the cold water is being designed to high velocity, there's more pressure drop because the pipe's smaller. Whereas on the hot system, the pipe is larger, so less pressure drop and less velocity. So one solution here is to add a pump to your design that will increase the pressure, and sometimes that's the right solution. But on a project like this, it doesn't make sense to add the additional cost of installing the pump and also maintaining it and having to replace it in the future. Whereas what we can do is we can look to increase the pipe size on the cold water system by decreasing the velocity. So if we come to the settings and under cold water, instead of designing to 1.5, we want to change that to 1.2 and click recalculate. Everything's going to update for us, and because the pipes have now increased to that 20 mil instead of 15, there's less pressure drop, less velocity, therefore we're getting sufficient pressure at the fixtures. So just important to know that if you are pushing your system design to a high velocity, there are benefits, but you've also got to be aware that there's more pressure drop for your system. So just like we mentioned at the beginning, there's definitely a good balance to be had, and that's why it's good to do your calculations, see what works, and your client's going to get the best outcome based on this. To summarize everything and to act as a checklist for your next calculation, the steps that you need to follow are to first choose your maximum velocity parameter and then choose your minimum velocity parameter. Once you have those selected, you can calculate your peak flow rate, and then you want to check the velocity against various pipe sizes. You're most likely going to choose the smallest pipe size below the maximum velocity parameter because this is the most cost-efficient one to install. You also then need to ensure that the velocity exceeds the minimum velocity parameter, and if it does not, you're going to have to communicate with your manager and the client just to figure out what the best solution is for your project. Some considerations are if poor water hygiene is a risk to the building's users, such as in a hospital, then you're not going to want to go below the minimum velocity. Then also, is a high velocity suitable with the manufacturer's recommendations and what your client's doing in the building? And if there's no room to move on either of those, you're going to have to look at something unique on your project, like maybe flushing. But I don't want to give you any solutions here because it's just really important to discuss this with project by project. And that is everything for today. So I hope this helps you in your future designs. If you've got any questions about the calculations or you'd like to know more about h2x's design software, you can reach me directly at jonathan@h2xengineering.com, or you can check out our website, h2xengineering.com, where there are lots of other technical resources just like this one.